Okay, hello everyone. This video is for the Abacus practice session of the modeling and simulation course. In this video, I will show you how to model the buckling of the composite component using the FEE method. So in this video, we will establish some local rectangular collision systems and also define the material orientations of the composite. So we will go through the tutorial sheet step by step. So the first step, we are going to create the part of this I-beam. So this is the ODB output or the simulation results of the buckling of this I-beam. So we go to the part module. We are going to create the geometry of this beam. So we hit create part and name it as part 1. So the type is deformable 3D shell, and we will model it by using the extrusion. The approximate size of this cross-sectional area of the beam is 400 mm, and we hit continue. Okay, so we are going to create the cross-sectional area of this I-beam by using 3 lines. So 2 lines for the upper and lower flank, 1 line is for the web of this I-beam. So we are going to use 2 points to define the lower flank of this beam. So we need to specify the coordinate of these 2 points. They are minus 50, and 50, minus 50. So this is a lower flank. The next step is define the web. So again, 2 points for the web line. 0, minus 50, and 0, 50. So the upper line is minus 50, sorry, it's minus 50, 50, and 50, 50. So here is a cross-section area of the I-beam. So we are going to extrude this cross-sectional area. So we need to specify the depth or the length of the beam. So we define it as 2000 mm, and we click OK. So here is the geometry of our I-beam. Since we need to define the different material properties for this composite, so we need to create 3 local coordinate systems for defining the material property. So we define the first local coordinate system as rectangular, and we need to specify the original point of the first local coordinate system. So it's 50, minus 50, and 1000. We need to specify another point on the x-axis of our first coordinate system. So it's 50, minus 50, and 0. So the third point needs to be specified on the xy plane for our local coordinate system. So it's 0, minus 50, and 1000. So here is our first local coordinate system. So we are going to use the same method to define the other 2 local coordinate systems. So again, the original point of the second local coordinate system is 0, 0, and 1000. And the point on the x-axis is the 0, 0, and 0. The third point on the xy plane is 0, 50, and 1000. The third coordinate system, original point is 0, 50, 1000, and 0, 50, and 0, and minus 50, 50, and 1000. Okay, we need to add the geometry here and repair the face normals. Select faces. Repeat this step until all the faces are turned into purple here. So after we add the face, we are going to define the material properties. Here we rename the name of the property as CRP and define it as elastic. Change the type as laminar because it's a kind of laminar structure of this composite. So we need to define the Young's modulus and of the composite in the fiber direction and the transverse direction. So in the fiber direction, the Young's modulus is 134 megapascal and 10,000 megapascal on the transverse direction. Position ratio is 0.25. Shear modulus 5,000. All the three shear modulus are 5,000 megapascal. We click OK. So we need to create a section of this material property, and then we can assign this material property onto each section of this beam. So section 1, we define the category as as shell composite, and we assign the material for all 8 layers as CRP. The thickness of each layer are all 0.5 millimeter. We need to specify the orientation angle of the fiber as for each layer. And section 2, the same configuration and the same material property for all 8 layers except the fiber orientation. The thickness are all 0.5 millimeter. Orientation angle of the fiber for each layer. The third section, the same configuration except the orientation angle of the fiber. Zero, 45, minus 45, minus 45, 45, 0, and 0. Okay. So the next step is we can assign the section onto this beam. So we assign the section 1 to the lower flank of this beam, and section 2 to the web of the beam. Also section 3 to the upper flank of the beam. Since it's a composite material with fiber orientation, so we need to assign this fiber orientation by using our previously defined local coordinate systems. So we use the local coordinate system 1 to define the lower flank of this beam. So the normal direction set as number 3 axis without rotation. The web, we select the second local coordinate system, the same configuration again. For the upper flank, we select the third local coordinate system. Okay. So next step, we need to create the assembly in the assembly module here, and we select the dependent instant tab. We click OK, and then we create a step for Abacus to run the job. So we set it as static but linear permutation and buck module. Here we select the number of eigenvalues as 1, and the maximum iteration is 200. So the Abacus will try 200 times for each iteration. And the next step, we are going to create some iterations. So in this module, we are going to create a reference point here and couple this reference point to the cross-sectional area of the I-beam. So this algorithm is used to lock all the degree of freedom of this I-beam to the reference point. So we need to specify the coordinate of this reference point as 0, 0, and 2100 here is our reference point. And we define the coupling iterations. We couple this reference point to all the lines of this cross-sectional area of the I-beam, and we constrain all the 6 degrees of freedoms. And the next step, we are going to create a load and boundary conditions. First, we need to apply the load onto the reference point here as concentrated force. Apply the force on this reference point. It means that we are applying the force onto the cross-sectional area of this I-beam, since this I-beam has already been coupled with this reference point. Here we got our force, and then we define our boundary conditions. We select the displacement and rotation boundary conditions, and we constrain this reference point. That means we constrain this cross-sectional area of this I-beam. We constrain all 6 degrees of freedoms except the translation degree sum on the z-axis here, because we apply the force on the z-axis, so we cannot constrain the degree of freedom of the z-axis. We hit OK, and we rotate our I-beam to constrain the another end of this beam, the same boundary conditions. But this time, we will constrain all the 6 degrees of freedom of another ending of the beam. Yeah. After we defining the boundary and loaded conditions, we can create our mesh. In this module, you can find your beam turned into the into the color of the pink. That means you need to change the mesh control algorithm to structure here. So in this scenario, we can assign the quadratic element type onto this beam. Before that, we need to specify the size of the beam to 10 mm. Okay, then we can create the mesh. And we need to change the mesh type to be standard linear but shell family. Okay. So now we can create the job for the Abacus to run the simulation. Everything is default. We name it as job 1. Everything is default. So now you can submit your job, and Abacus will run the job automatically for you. So here I already got the ODB output here. So in this module, you can see the deformation of this beam in the buckling mode. You can select the deformation here. So if you want to capture the ODB output, capture the picture of this ODB output, you can go to File Module and select Print, and change the destination as File and name it as what kind of name you want, and click OK. It will save this picture into the specified direction. And if you want to save this CE file, you can go to File Module and hit Save. Save it at CAE. So it will basically save the final element model for you. So here is all about the final element process of this section. So if you have any questions, please raise your hand and our teaching assistant will come to you. Okay, so thank you for watching.